Hi everyone, this is Mohamed from Monash University. Thank you for attending my session today. This work is about the study of the automated process-induced residual stresses in the multi-axis composite laminates. This work has been done by Mohamed Ammar, myself, and Professor Bijan Shirinzadeh in the Robotics and Mechatronics Research Laboratory in the Department of Mechanical and Aerospace Engineering at Monash University, Australia. The outline of this work, I'm going to talk about the background first, and then we'll talk about the current state of the composite produced by the robotic fiber placement or the automated fiber placement. And then I'm talking in details about the robotic manufacturing and trajectory generation algorithm that we are using in this work, and then the attitude degree of freedom module that we are using also in this work. And we'll continue with the experimental procedures, and then we'll talk about the results and the discussion out of this work, and then we'll end up by the conclusion. So first of all, regarding the composite manufacturing, it starts by the traditional methods using the hand layup, as you can see here, and also this type of methods was time consuming, was labor intensive, and also low efficiency and hazardous. So that's why more or advanced manufacturing techniques has been introduced, such as the automated tape laying using the machine, as you can see, and is using controlled consolidation here on the left hand side. And this actually use multi-axis machine, and this couldn't be used for curved structure, only used for the flat structure. And then there is the filament winding, and this by sticking the fiber on the different shapes, and this also couldn't be used for a concave shapes, and this depending on the friction between the fiber lines and the mold itself to secure the fibers on the outside surface of the mold. And eventually, the robotic fiber placement technique has been introduced to manufacture all the complex structures. And this particular technique is high accurate, as this is using robotics manufacturing. So it's using an industrial robot to make the manufacturing process, and it's high, which gives high flexibility and also cost effective, as it's less labor cost, and also it's a fast process. That's why we are using in this work the robotic manufacturing techniques using industrial robot Yaskawa Motoman SK120. And this robot has a workspace from 896 to almost 2500 millimeter, and this can apply up to 120 kilograms. Um, as you can see here, we have industrial robots. It's integrated with a robotic manufacturing head to provide a fully controlled process for composite manufacturing. So in this robot, we are making a trajectory generation, and we're introducing an algorithm to manufacture the laminates with different directions. So we are introducing four different directions: 90 degrees and 0 degrees, and also 45 and minus 45 degrees. So we are moving the end effector in different direction with respect to the mold or the tool to be able to have different direction of the fibers. So we have a fully controlled pre-programmed process that can make the fiber laying in different or lay up in different directions. Then we have a complete attitude degree freedom module based on this compaction roller, which moves in three directions. And we have a pneumatic system here on the top of it to apply the pressure on the laminates or the deposit laminates to provide a full consolidations of the layers. So based on this algorithm here, you can see here we are introducing a normal and even force on the whole layers area. So as we are moving by, or as the robot moving by the compaction roller, it's always introduce the same force with the same direction based on this introduced algorithm. So there is angle theta here. Based on this angle with each increment, there is an auto correction of the robot control based on the sensory feedback control system to make these auto corrections to the force magnitude and the force angle. Then we are using offline programming here in this work. So we are using pre-programmed trajectories. So we are building the programs first based on the language robot or the robot language informed tool. So we are using all this or uploading all of this application to the robot itself using a software FC1. And we also make an inverse kinematics in this work for for this robot. This robot is 6-axis robot, so you can see here we have 6 variables, 6 rotational angles for each joint, and then we make this based on the DH rules. We make the inverse kinematics for the current robot. So the parameters of the robotic fiber placement, we have some inputs and we have some outputs. For the inputs that we can control in this process, we can control the curing procedure, and also we can control the heating based on the robotic fiber placement head itself, and also we can control the compression force and the fiber directions, and also we can change the fiber resin types and the ratios. The output coming out of this process, the voids and the cracks based on changing all of these parameters, we can have different voids and the cracks inside the material, and also the failure behavior for each fabricated laminates will be different, and the surface roughness will be different as well based on the conditions of the process, and the residual stresses, which is the main work for today, also different based on the different conditions, and the strength and elasticity of the material will be also different. So we are fabricating the samples first, flat samples with different directions. As you can see here, there's a robotic fiber placement head with the compaction rollers acting on the specimens here, and we have a hot gas torch to supply heating to make the deposition of layer by layer on the top of each other. And we have the pre-prick tools here sourced from the tools to the robotic heads. And we have the force torque sensor between the end effector and the head here, which provide the feedback control system. So after we getting these samples here fabricated, we putting it in a fully controlled autoclave with a controlled pressure and temperature to make the full curing for the samples. Then we are evaluating the robotic fiber placement induced residual stresses using the mechanical way, which is the incremental hole drilling method, based on 3 steps. First of all, we are measuring the relaxation strains using this setup here of the hole draining apparatus. And then we are calibrating the measurements of the relaxation strains using the finite element analysis. And then we are using these results with the analytical formulation to be able to calculate the residual stresses itself. So in this work, we have different laminates configurations. So we fabricate different, as you can see here, 6 configurations with different angles. Each of these has 8 layers. We put here the first 4 layers, and the other 4 layers had the same directions. So we change the direction, and then we need to see the effect of this change on the fabricated samples, in particular the residual stresses induced inside the samples. So from the structure analysis and the first results of this work, you can see here in the top parts is two photographs here, coming out of the scanning electron microscopy. So you can see here we has two successive layer with the same direction, and here the same. So you can see that the amount of voids inside this or between these two layers and here between these two layers are lower than the bottom two photographs, which has two successive layers with different or the change in the fiber direction. So you can see all of these are voids between the two layers, and the same here, these two voids or this void between two successive layers with different direction of the fibers. So you can see here changing the direction, increase the porosity of the material or increase the internal voids inside the material. Accordingly, on the effect on the residual stresses, once we have more voids or less voids, the bonding between each two successive layers increase. That's why the restriction between the layers increase, which induce more residual stresses. So you can see here for that between A and D, for A, we have two layers, minus 45 degree and minus 45 degree, and 45 and 45, and then the other one, 45, and then minus 45, and then 45, and then minus 45. We can see here in the top one, in A, part A, we have more residual stresses. So the maximum residual stress here induced in the first laminate because we have two successive layers with the same directions. But in the second part, we are changing the direction with each layer. That's make decrease in this um, uh, values of residual stresses. The same here, we can see that we if we have like 0 0 degree and 90 90, and instead of that 0 90 0 90 degrees, we can see that there is increase in the values of the residual stresses if we have the same direction for the successive layers. So, just for your information, that all of these samples has been manufactured under the same conditions with the same temperature and the same pressure and the same placement speed. So the only effect on this residual stresses type was the change in the configuration, and the reason for that because mainly because that we have more restriction layers with the same direction layers laminates. So in conclusion, robotic fiber placement it includes many factors that can affect the composite quality and the formation of residual stresses inside the structure. So this paper describes the effect of the configuration of the laminates on the induced residual stresses. Robotic manufacturing is performed using a 6 degree of freedom work cell. The trajectory of the robot's end effector are calculated based on the feedback control system. Then the workpiece are cured inside the autoclave. So as a result, a noticeable increase in the internal voids are detected with changing the layers directions, and also an increase of the residual stresses have been induced more with the successive layers have the same fiber direction. In a future work, we will do more studies on the effect of the configurations as well as the type of the fibers posed at the same time. We'll study their effects on the induced residual stresses. Thank you, and that's all for today. Thank you so much for your attention.